Welcome to Meringues. We're going to discuss the chemistry involved in making egg foams, how soap bubbles form, and what hot air balloons can teach us about cooking. Let's get started. We've talked in previous videos about how the egg proteins denature and bind together when heated. This process turns the liquidy protein and water mixture in the albumin, the egg white, into the network of proteins that traps the water molecules in place to form a semi-solid gel-like mass that we see in a cooked egg. But heating the egg isn't the only way to alter the protein structure. We can also do so by beating the egg. Now, with most substances, physical agitation such as whipping tends to break down extended structures into smaller bits. For example, if you take a weed whacker to a pile of leaves, you're going to end up with lots of tiny bits of leaves. But when egg whites are beaten, instead of breaking down, larger extended structures are formed. That is, we get an egg foam. Egg foams come in a few different varieties, including meringues, mousses, gin fizzes, soufflés, and sabayons. We're going to get into each of these dishes in a little bit more detail later on, but first let's discuss, in general, what happens when we make an egg foam. Similar to the foam on the top of a beer or a cappuccino, egg foam is composed of gas bubbles trapped inside walls of liquid. The gas bubbles are the air that has been incorporated as the whisk drags the air through the egg liquid. Now, when you whisk water, the bubbles that form pop so quickly that it's difficult to even see them forming. The proteins in the egg white form the structure of the walls of the bubble. The properties of the structure of the bubble walls determines how long the bubbles last, and thus how long the foam remains. So the addition of the albumin proteins to the water is what allows the bubbles to last long enough for a foam to form. Let's take a minute to talk about surface tension and how it affects bubbles. Water has a very high surface tension, which causes three-dimensional puddles to form on surfaces, such as that shown on the top right. If water had a lower surface tension, it would have a greater tendency to form a wider, flatter puddle, more effectively wetting the surface. When a drop of water is in zero gravity, such as when an astronaut on the International Space Station forms a small droplet floating in the air, the droplet quickly forms a spherical shape. This spherical shape minimizes the surface area of the droplet and maximizes the average number of other water molecules surrounding each individual water molecule. But when a droplet is falling through the sky, the air resistance causes a pointed tail to form on the trailing edge of the droplet, that is, on the top side. The combination of water's surface tension and air resistance is why a raindrop has the shape that it does. And surface tension also causes water to form a meniscus when placed into a glass tube. The water is attracted to the glass, so it maximizes the area of interface between the glass and the water. This causes the water at the edge of the tube to rise up the sides of the tube. But the surface tension pulls other water molecules not directly next to the glass along for the ride, forming the concave curve in the water's surface. If the walls of the tube are narrow enough, such as in a drinking straw, this surface tension can pull the surface of the water inside the straw up above the level of the water on the outside of the straw, as shown on the bottom right. And if you've ever eaten a bowl of Cheerios in milk, you might have noticed that the individual Cheerios seem to be attracted to the edges of the bowl as well as to each other. This is because the milk in the bowl is forming a very shallow meniscus, such that the surface of the milk at the edges of the bowl is slightly higher than the surface in the center of the bowl. Since the Cheerios float in the milk, they'll naturally float upwards on this tilted surface until they hit the side of the bowl. But the milk surface also curves upwards slightly around each individual Cheerio, so other Cheerios will experience a similar effect when nearby, causing the Cheerios to seem to stick together. And finally, surface tension allows for small creatures to engage in what we call water walking. Some insects can walk on water without getting wet. Their small weight can be offset by the force from the surface tension as their feet gently press down on the surface of the water. In the image shown on the left, you can see the dark spots around the insect's feet as the water curves down from the weight of the insect and so doesn't reflect the light from the sky. But as long as the insect isn't too heavy, water's surface tension is able to exert a stronger force than the weight of the insect, and the insect's feet don't penetrate through the water's surface. There are also some small lizards that are capable of running on the surface of standing water. Here's a link to a short video about a Jesus lizard which can run across water. I'll also post this link in the description below. Now, the lizard is too heavy to stand still upon the water's surface. That is, if he stops moving, he'll sink into the water. But so long as the lizard's feet move fast enough, he can press a foot down into the surface of the water and then pull it back up before the water collapses around his leg. Unfortunately, even the fastest human is far too slow to move their leg fast enough to accomplish this. Although there is a Mythbusters episode in which Jamie tries to walk on water in a similar manner. Spoiler alert, he gets wet. Again, water's high surface tension is a result of the very strong intermolecular forces holding neighboring water molecules together. I've shown here a droplet on a surface, and inside the droplet are beige circles representing individual water molecules. Each water molecule has a variety of arrows showing the attractive force it feels pulling it towards its nearest neighbors. For the molecules in the center of the droplet, those forces will roughly cancel out. That is, for each arrow pointing left, there's an arrow of a similar magnitude pointing right. For each arrow pointing up, there's one pointing down, and so on. But let's look at a molecule on the outer surface of the droplet, such as the one on the top. There are some red arrows, one pointing left and one pointing right. Again, these attractive forces towards other molecules on the surface of the droplet will cancel. However, the black arrows representing the attractive forces pulling the molecules down are not balanced by equivalent arrows pulling the molecule up because there are no water molecules above this one. This means that the molecule experiences a net force pulling it down towards the center of the droplet. As a result, it will accelerate towards the center of the droplet until it either collides with another water molecule that bumps it back up towards the surface, or it will slip between the molecules in that second layer, and another molecule will take its place on the surface. Similarly, the water molecules on the far left and the far right of the droplet experience a net force pulling them towards the center of the droplet. It's this force that prevents the droplet from expanding sideways to cover more of the black surface below. Okay. So water has a high surface tension. What does this mean for a bubble? When an air bubble forms in pure water, that high surface tension causes the water molecules to pull together. This quickly forms a hole in the bubble wall, and the bubble pops, allowing the air trapped inside to escape. But if we add other molecules between the water molecules in the bubble wall, we can decrease the surface tension, allowing the bubble wall to last longer. Furthermore, if these added molecules also make the water more viscous, that is, less runny, then the bubble walls will last even longer as it takes longer for the water molecules to move through the more viscous fluid. It turns out that the proteins in the egg white accomplish both of these. When the proteins in the egg white are subjected to physical stress, they tend to unfold and bond with one another. That is, the physical act of dragging the whisk through the liquid drags water molecules along with the wires of the whisk. Those dragged water molecules pull on the proteins to unfold them. The whisking action also incorporates lots of air bubbles into the liquid. Now, the chemical environment of the air bubbles is much different than the chemical environment of the water. That is, the water molecules are highly attracted to each other, but minimally attracted to the molecules in the air, plus the density of molecules in the air is roughly 1,000 times lower. The difference between these two chemical environments tends to further unfold the egg white proteins. Those unfolded proteins tend to gather at the interface between the air and water. This allows those proteins to align so that their hydrophilic ends face towards the water and their hydrophobic ends face towards the air. The hydro part of hydrophilic means water, and the philic part means loving. So something that is hydrophilic loves water. That is, it's attracted to the water. On the other hand, phobic means fearing, so something that is hydrophobic avoids water. That is, it's repelled by the water. So these proteins have one end that is attracted to water and another end that's repelled by the water. The proteins naturally arrange themselves such that the hydrophilic ends point towards the water, and the hydrophobic end points towards the air on the inside of the air bubble. We can see a similar effect if we change the attraction of a surface to water. With a hydrophilic surface, the strength of the interactions between the surface molecules and water molecules is high, and the water spreads out to wet the surface. On the other hand, with a hydrophobic surface, the strength of the attraction between the molecules in the surface and the water molecules is low. so low that the water molecules are far more attracted to other water molecules, and the droplet forms a much more three-dimensional shape that minimizes contact with the surface below. Now, hydrophilicity isn't an all-or-nothing property, it's a gradient. So, a surface could be moderately hydrophilic or moderately hydrophobic, in which case the shape of the droplet on the surface would be somewhere between these two extremes. In recent years, chemists have developed a variety of different superhydrophobic substances. A few of the products made include Neverwet, Super Everdry, and Rain-X. In each of these images, one surface has been coated in the superhydrophobic substance and the other surface remains untreated. The water-based liquid is repelled from the treated surface and easily runs off rather than wetting the surface. For example, in the case of the two men shown on the right, the man whose clothing was treated is left virtually spotless after being splashed with muddy water, while the man on the left looks about as you would expect. These products do work quite well on certain surfaces. However, the hydrophobic coating tends not to last terribly long, especially if the treated object will be exposed to washing with soap, as would be the case with clothing. This makes these products relatively expensive for the protection that they provide. However, one product that appears to have become quite popular is Rain-X, a hydrophobic coating marketed for automobile windshields. Now, I'm not endorsing Rain-X specifically, and there are a variety of other similar products on the market, but I do use it on my vehicles, and there is a substantial improvement in visibility in the rain. For the low cost, the improvement in safety when driving in the wet is significant. Like these other coatings, it will have to be reapplied periodically, but I've found that the effect can last a number of months. The cells in your body all have a cell membrane that acts to keep the stuff that should be inside the cell on the inside and the stuff that should be on the outside of the cell on the outside. This cell membrane is made up of lots of phospholipids. The term lipid is a word used to describe molecules that are fats or oils. As with other oils, these phospholipids have a long, hydrophobic tail that is repelled by water. But the phospho part contains the polar phosphate group, and so is hydrophilic, and we call this the hydrophilic head. As a result, these phospholipids have one end of the molecule that is attracted to water, the hydrophilic head, and another end that is repelled by water, the hydrophobic tail. When a bunch of these molecules are near each other, they spontaneously arrange to form a double layer, with the hydrophobic tails pointing inwards towards each other and the hydrophilic heads pointing out towards the water, either inside or outside the cell. The double layer of hydrophobic tails serves to keep water and other polar substances from moving through the membrane. There are typically special structures embedded in the membrane that allow transport of these types of molecules across the membrane, but those are really outside the scope of this class. Oil is hydrophobic, and water is, of course, hydrophilic. As a result, oil and water don't mix well. The hydrophobic oil molecules all clump together and, due to the lower density of the oil than the water, float on the surface of the water. But if we add a detergent, we add a molecule similar in structure to the phospholipids that allows the oil to dissolve into the water. That is, detergents have a hydrophilic head and a hydrophobic tail. Like the phospholipids in a cell membrane, the detergent molecules self-assemble into a spherical structure. However, instead of forming a double layer, the detergent molecules form a single layer, with the hydrophilic heads pointed outwards and the hydrophobic tails pointed inward. The hydrophobic oil molecules are attracted to the hydrophobic end of the detergent molecules, and so they form a droplet inside the sphere of detergent molecules. But because the outside surface of the detergent sphere is hydrophilic, it's attracted to the water molecules, and so it dissolves well into the water. As I'm recording this video in the summer of 2020, the SARS-CoV-2 virus, the coronavirus that causes COVID-19, is rapidly spreading throughout the United States. This virus is an encapsulated virus, which means that the virus is enclosed by an envelope roughly analogous to a cell membrane. That envelope is made up of a variety of lipids that assemble in much the same way that we've just seen. When soap molecules encounter this virus envelope, the lipids from the envelope mix with the soap molecules to create micelles, as we saw with the oil. However, this breaks the virus particle open, effectively preventing it from infecting human tissue. As a result, the simple act of washing your hands with soap and water serves as a powerful way to reduce the likelihood of infection of yourself or others exposed to surfaces that you might touch by eliminating most of the virus particles from your hands. Even if you're watching this video in a region or time when this particular virus is no longer a threat, this effect remains effective against virtually all viruses, bacteria, or other microbes that can cause illness in humans. So please make it a habit to regularly wash your hands with soap and water to reduce the spread of all types of infections. Okay, back to eggs. The proteins in the egg white arrange in a similar manner around the air bubbles with their hydrophilic ends pointed towards the water in the bubble wall and the hydrophobic ends pointed towards the air inside the bubble. Now, as those proteins arrange themselves in the bubble wall, they form bonds with one another. These bonds allow the proteins to link together to form a loose structure that increases the stability of those bubble walls, allowing the bubble to exist for more than just a few seconds, as would be the case for pure water. However, given enough time, those bonds between proteins will break, destabilizing the bubble wall enough so that the bubble pops and the foam settles back down. If we want to make the egg foam permanent, then we need to stabilize the bubble wall structure enough that it becomes essentially permanent. We can do this in a few ways. One way is to add other ingredients such as flour, cornstarch, chocolate, or gelatin. Or we can heat the proteins, causing them to denature and form even more chemical bonds between neighboring proteins. This second way works because of ovalbumin, which is the major protein in the albumin. Ovalbumin does not unfold during the beating process, but it does unfold and coagulate when heated. So if we heat the egg foam, the addition of the ovalbumin to the extended protein network more than doubles the strength of that protein network. Furthermore, heating the egg foam also causes some of the water to evaporate, increasing the viscosity and thereby further stabilizing the bubble walls. So we've seen that the egg white proteins stabilize the bubble walls and thus stabilize the egg foam. But those same proteins can also destabilize the bubble wall and egg foam too. As we beat the egg white, the proteins stabilize the egg foam by binding together as we've discussed. However, if this process continues and the proteins bind together even more strongly, they tend to squeeze out the water molecules. Eventually, this causes the proteins to curdle and clump together into solid, grainy particles suspended in the water. But now those bubble walls are mostly composed of water again, and so they will be relatively weak and the egg foam will collapse. So to make a good egg foam, we need to either beat the egg white enough to form the foam and then stop, thereby stopping the further coagulation of the proteins, or we need to limit the protein coagulation so that they can't coagulate to such an extent that they'll begin to destabilize the foam. We can limit the protein coagulation using copper utensils, a copper bowl, or even a copper powder supplement. However the copper atoms are added to the egg foam, the copper atoms bind to reactive sulfur groups in the proteins and prevent them from binding to other protein molecules. This eliminates the strongest protein-protein bond that can form, so the protein network can only get so strong. However, there are a few downsides to using copper. The first is that copper is relatively expensive. Now, I don't mean that it's expensive compared to gold or platinum or other precious metals. After all, we use copper for a wide variety of things, including wires in our homes and electronic devices, in water and air conditioning pipes, sometimes on roofs and gutters, and more. But it's not super cheap either. Sometimes thieves will steal these items to sell for scrap. Additionally, copper is relatively difficult to clean, and it's because of those very same strong copper-sulfur bonds. These are relatively strong bonds, which means that they're relatively difficult for us to break when trying to clean the copper dishware. As a result, it's much easier to clean plastic, glass, or steel bowls, and so most people will use these materials in their cookware. We can also limit the protein coagulation using acid. The strong bond between proteins forms when two sulfur-hydrogen bonds break, and a stronger sulfur-sulfur bond forms. But we can make it less likely for a sulfur-hydrogen bond to break by increasing the number of free-floating hydrogen ions, that is, by decreasing the pH. Two common acids to add per egg white are 1/8 teaspoon of cream of tartar, remember this is tartaric acid, or 1/2 teaspoon of lemon juice, in which case the primary acid will be citric acid. Now, the ways we've just discussed aren't the only ways to limit the protein coagulation. In fact, there are some ingredients that will prevent the formation of a good egg foam. These include the egg yolk, oils and fats, and detergents. As a result, we need to avoid having any of these in the bowl with the egg white. All of these have hydrophobic portions in the molecules, and so they'll compete with the egg white proteins for space at the air-water interface. However, they won't form bonds between neighboring molecules like the egg white proteins will, and so they won't contribute to the structure of the bubble wall. Now, the presence of yolk, oil, fat, or detergent won't completely prevent the formation of a foam, but it will make you work harder to form the foam, and it will make the foam be less light and stable. However, once the stable foam has been formed, we can add yolk or fat without significantly altering the structure of the foam. So you can make a dish with these ingredients present, you just have to wait to add them until you're satisfied with the foam. As we've discussed before, salt ions can interfere with the binding of the egg white proteins. So if you add salt, you'll have to work harder to make the egg foam, and your foam will be less stable. This means that it's usually going to be better to just add the salt to other portions of the dish. That is, the egg foam is rarely the only component of your dish. Rather, it's just one of a few distinct portions or layers, as is the case with the meringue that we'll make this week as it sits atop the lemon pie filling, which itself sits atop the pie crust. Adding the salt to other portions or layers means that when you eat the combined dish, you'll taste both the salt and the egg foam in the same bite, despite the salt not being incorporated into the foam itself. Sugar in the egg foam can be both helpful and harmful depending upon when it's added. If we add sugar early in the process before the egg foam is formed, the sugar delays the foaming and reduces the overall volume and lightness of the foam. This is because the increase in viscosity of the sugar-egg mixture makes it harder to spread into the thin bubble walls required for a light and voluminous foam. But if we add sugar later, the sugar can increase the foam's stability. That same increased viscosity slows the drainage of liquid from the bubble walls and thereby slows the coarsening of the texture of the foam. In addition, the sugar molecules slow the evaporation of water during cooking until the ovoalbumin has coagulated, so fewer bubble walls will pop prior to being permanently set by the heat. Furthermore, once the water does evaporate, the sugar forms long, cotton candy-like strands of solid sugar crystals which serve to further stabilize the structure. So adding sugar early will interfere with the foam, whereas adding sugar after the foam is formed improves its stability. This is just one reason why the order in which you mix ingredients can have a significant impact upon your finished dish. Water generally isn't used in egg foams. By this I mean additional water added to the bowl, since the egg white itself already contains a significant amount of water. Adding just a small amount of water can increase the volume and lightness of the foam as the water dilutes the egg white proteins in the bubble wall. A little bit of this dilution makes it a little easier to incorporate the gas bubbles into the liquid. But as more water is added, the rate at which liquid drains from the bubble wall becomes higher and the foam becomes less stable. Once the egg white is diluted by 40%, it cannot produce a stable foam at all. Okay, we're now going to get into how to produce the best egg foams. However, you can produce a decent egg foam with virtually any egg, whisk, and bowl, at least as long as you avoid adding any of the ingredients we've already discussed that limit egg foam formation. Note here that a whisk is strongly recommended over a fork because the whisk has a much higher surface area and so it will incorporate many more air bubbles than the fork, and those air bubbles will be smaller on average. A handheld electric mixer or stand mixer will also work just fine. Now, I have had students successfully make the meringue with a fork, so it's not that it can't be done. But if you're mixing by hand, a whisk will work much better and faster, and so your forearms won't get nearly as tired. Old eggs have thinner whites and thus foam more rapidly. In fact, very fresh eggs are nearly impossible to foam by hand. However, these fresh eggs are also less alkaline, and so they'll make a more stable foam. Note here that by old eggs, I mean eggs a few weeks old. In most cases, it will take a few days for an egg to make it to the store shelf after being laid by the hen, So if you're using an electric mixer, the difference between new eggs and old eggs will be an extra minute or two of mixing. But if you're mixing by hand or using an egg that was laid this morning by a hen in your own backyard, this difference will be more significant. Now, cold yolks are less likely to break upon opening the egg, but to produce the foam, the egg white should be room temperature. So, should you use a cold egg or a room temperature egg? Well, a cold egg white from the refrigerator will quickly warm to room temperature during the beating process. So, you're best off using a cold egg to minimize the yolk breakage. However, if you're using multiple eggs, best practice is to open each egg into a small bowl rather than the larger mixing bowl. After opening each egg, being careful to keep the yolk from mixing with the egg white, transfer the egg white to the larger mixing bowl. This way, if you do accidentally mix in a yolk with one egg, you're only throwing away one egg rather than the entire bowlful. Well, really, I hope that you use that egg in another dish rather than throwing it away entirely, but you get the point. The bowl you beat the egg whites in needs to be big enough to allow for plenty of volume expansion of the foam. The bowl should be at least 8 times larger than the egg white volume. For example, to make the meringue this week, you'll use 4 egg whites with a volume of roughly half a cup. This means that your bowl needs to be at least 4 cups, that is 1 quart, and a little bigger would be a little bit better to reduce the likelihood of spilling. If you're using a plastic bowl, be sure to wash the bowl well with soap and then rinse it quite well to avoid getting any fat or soap into the egg white. This is a larger concern with plastic bowls because plastic has a chemical structure similar to the fats and soaps, and so it tends to trap thin layers of these chemicals on the surface of the bowl. Usually, a thorough cleaning with soap and hot water generally gets a plastic bowl clean enough, although I've found that quickly wiping them down with a cloth towel helps too, as the fibers of the cloth trap the fat or soap molecules. The larger the whisk, the larger the fraction of egg white that will be beaten with each stroke, so a bigger whisk is better. This is the same reason why the whisk is preferred over the fork. In general, electric mixers will make mixing and beating ingredients easier, but this is especially true for making an egg foam since the time required to beat is so long. A stand mixer is similar to a handheld electric mixer, but the stand mixer typically uses a planetary orbital motion similar to that shown on the right to incorporate a larger fraction of the bowl contents. That is, the stand mixer automatically moves the whisk around in the bowl as you would with a hand mixer. This allows you to have the stand mixer work away while you move on to another task in the kitchen. So whether you're beating by hand or using an electric mixer, how do you know when to stop? There are a few different ways to tell when the foam is at its optimum condition. One way is whether or not the structure is strong enough to hold up a penny or an egg. Another way is in how the foam supports its own weight, that is, in soft mounds or sharp peaks, or whether the foam clings to the side of the bowl or slides down the side of the bowl. Yet another way is whether the surface looks glossy and shiny, or if it looks dry and dull. Whichever method you use, the method helps identify how crowded the air bubbles are and how much lubrication they have between them in the form of liquid from the egg white. Some dishes require more lubrication with a greater tolerance for expansion when heated, while others require greater stiffness to better hold their shape. I've shown here 3 different stages of the egg foam. On the left, the egg foam has begun to form, but the large bubbles and flat surface within the bowl show that the foam is still quite liquidy. Note that you can see trails where small droplets of foamy liquid have run down the inside surface of the bowl. In the center, we've developed the foam to the soft peak stage, in which the foam is now stiff enough to retain some 3-dimensional shape, but it's still soft enough that the peak droops under its own weight, and the ridges in the foam get dulled somewhat as the peaks slowly relax into more rounded shapes. There is still plenty of lubrication in the bubble walls that allows the bubbles to slowly slide past one another, causing the drooping or rounding of those edges. On the right, the foam has reached the stiff peak stage, with enough structure in the bubble walls that the bubbles no longer slide past one another. So we now have a sharp, pointed peak when we remove the whisk, and well-defined ridges farther down, showing the paths that the wires in the whisk took most recently through the foam. In this stiff peak stage, the foam is stiff enough to hold its shape and stick to the sides of the bowl. In fact, it's often sticky enough that you can turn the bowl upside down without losing any foam. The surface is still shiny or glossy as the proteins and the water are still occupying a single phase. That is, the proteins have not yet curdled or coagulated into solid clumps. This is the stage that we want for mousse, soufflé, sponge cakes, and other dishes that require mixing and further expansion in the oven. At this point, the foam is over 90% air by volume with very thin walls for the bubbles. That is, the foam is quite light. If we continue beating after the stiff peak stage, the foam gets firmer and takes on a dull, almost dry appearance. The consistency gets crumbly and liquid begins to leak away from the foam, causing it to slide down the sides of the bowl again. This happens because the proteins in adjacent bubble walls are becoming bonded so strongly that they squeeze out the liquid between them. That is, they're starting to coagulate into solid bits of protein and liquidy water, although the proteins still encapsulate the air bubbles. Pastry makers aim for this stage to give them the firmest egg foam for meringue or cookie batter. Adding sugar at this point stops the protein coagulation and soaks up the excess water. Whichever stage you've gotten the egg foam to, if you leave it for long enough without setting it, it will eventually collapse as the air bubbles slowly pop and the material in the bubble walls collect as a dense liquid like you had at the start. To keep the light, fluffy foam texture, we need to set the foam in one of a number of different ways. We'll usually use one or more of heat, fat, gelatin, flour, or sugar. Let's now turn to the specific types of egg foam, starting with the meringue we'll make this week. A meringue is a sweet egg foam on its own and is generally used as a discrete element in a dish. That is, we can usually see the meringue as a separate component within the larger dish. For example, as a sweet, frothy topping on a pie, similar to how we might use whipped cream, which itself is a foam made using the proteins from milk rather than from an egg, or as a creamy icing, such as on a muffin or a cupcake, or perhaps as a hard edible container, such as when two hard-baked meringues are glued together using a filling, or perhaps as a decoration, such as the piped meringue on this cake, making it appear to be covered in lots of colorful chocolate kisses. Meringues can be either cooked or uncooked. The uncooked meringues are generally quite moist since none of the water has evaporated. The cooked meringues can be either syrup-cooked meringues, that is, meringues cooked to low temperatures such that only a small fraction of the water has evaporated. These have a syrupy texture to them. Or they can be so-called cooked meringues, that is, cooked to a higher temperature such that much more of the water has evaporated, creating a rather stiff texture similar to a cookie. Note that only a fully cooked meringue gets the egg foam hot enough to kill all salmonella bacteria that may be present. The type of meringue we'll make this week is a fully cooked meringue. Bear in mind, however, that it's still possible to experience salmonella poisoning if the entire foam did not reach 160 degrees Fahrenheit. So, if you have a suppressed immune system, you may wish to avoid the meringue or ensure that all portions of the foam reach temperatures above 160 degrees. So, what are some common problems cooks see with meringues? If the foam is underbeaten or overbeaten, it may leak syrup into beads or puddles as shown here. Similar beads can also form if the sugar isn't completely dissolved, as the solid sugar crystals attract water to make a concentrated syrup droplet. This second effect of absorbing water from the air is particularly prominent in humid environments, such as often occurs here in South Carolina. If enough water is absorbed from the humid air, the surface becomes soft and sticky. As a result, meringues should be kept in an airtight container until shortly before serving. Any undissolved sugar can also cause a gritty texture even if it doesn't cause the absorption of water from the air. Even if tiny crystals are left undissolved, they can slowly grow over time as more sugar crystallizes out of solution. As these crystals grow larger and larger, they'll become more and more noticeable, as biting into a meringue with lots of sugar crystals will be similar to chewing on sand. As my daughter discovered for the first time I took her to the beach, this is not fun. Another common problem encountered with meringues is if the oven temperature is too high, the coagulation of proteins occurs so quickly that water is squeezed out faster than it can evaporate, and syrup beads similar to what we saw before will form. Furthermore, the foam can rise and crack and turn the surface yellow instead of the bright white color of the raw foam. Now let's turn to mousse. Mousse is an egg foam that's stabilized using fats and gelatin protein. The fats and gelatin congeal at cold temperatures to help the egg foam hold its shape. The texture is similar to pudding, but is not as dense due to all of those air bubbles. Now, chocolate mousse is the most common flavor of mousse. Remember that cocoa butter is largely fat, and this fat congeals at low temperature to help stabilize the egg foam structure. When we eat the chocolate mousse, the cocoa butter melts again to give us the same creaminess that we love in chocolate as it melts in our mouth. Soufflés are another egg foam. When the egg foam is heated, the air bubbles inside expand. A soufflé takes advantage of this property to have the foam rise above the containing dish. You can see here 2 different soufflés that have each risen above the walls of their container. This makes the already light egg foam even less dense. Now, this expansion of hot air was first discovered by French scientist and balloonist Jacques Charles. Charles noticed that the volume of a gas increases linearly with temperature. This increase in volume upon being heated causes the gas to have a lower density than it did when it was cold. So if the air inside a balloon is hotter than the air outside the balloon will experience lift as the hot air will naturally float above the colder, denser outside air. We now call this relationship between volume and temperature Charles's law. But there's one more important implication of Charles's law. Clearly, as we increase the temperature, the volume of the gas increases. But what happens when we decrease the temperature? Well, naturally, the opposite happens. The gas contracts and the volume decreases. Now, when we're increasing the temperature, there's no upper limit to the volume. The gas can simply keep expanding as the temperature goes up. But when the volume is going down, can it similarly keep getting smaller and smaller forever? No. At some point, we've decreased the temperature enough that the volume of the gas is now 0. The volume can't become negative since the gas can't occupy less than no space. Furthermore, if we plot a similar line like the one shown here with a variety of different samples of gas, we find that the temperature at which the extrapolated line reaches a volume of 0 is always right around the same temperature. Early experiments put this temperature at around negative 285 degrees Celsius or about negative 481 degrees Fahrenheit. This was our first indication that temperature had a value at which we couldn't lower the temperature any farther. That is, this is our first indication of absolute 0. Now, we've since found that absolute 0 is at exactly negative 273.15 degrees Celsius or negative 459.67 degrees Fahrenheit. So what does Charles's law mean for soufflés? Fortunately, it means that as long as you've got air bubbles in your egg foam, those bubbles will expand when heated. And the higher we get the temperature of those air bubbles, the more they'll expand. Unfortunately, it also means that those air bubbles will also contract when they're cooled after the soufflé is removed from the oven. Fortunately, though, we can cause the air bubbles to expand again if we heat the soufflé once more. However, we can't keep expanding and contracting our soufflé ad nauseum. As water evaporates from the egg foam and the protein structure sets with heating, the extent of expansion and contraction will decrease with each cycle. So in the end, you'll want to eat your soufflé shortly after it's removed from the oven the first time and minimize the cooling and therefore the contraction of the gases that occurs. Alright, up until now we've been discussing the egg foams formed from the albumin, the egg white. And we've said that the egg white foams relatively easily because of all those proteins present unfolding and binding together to provide structure for the bubble walls. But the yolk has almost as much protein as the white does. Does that mean that we can form an egg foam from the proteins in the yolk too? Unfortunately, the answer is kinda. The yolk doesn't have enough water to form a foam by itself. You can form a foam from the yolk, but you'll have to add about 2 teaspoons of water per yolk. However, the foam from the yolk won't last nearly as long as foam from the white. The egg white proteins unfold with whipping, but the yolk proteins are more stable with regards to physical agitation, and so they don't unfold. So the yolk foam will have to be cooked to stabilize it. Furthermore, the added fats that come with the yolk mean that the proteins will be fighting for space at the air-liquid interface. As we saw earlier, this means that the foam will be weaker still.